Okay, good afternoon. After having a good trip of the countryside of a very beautiful country like Costa Rica, we are now all set to start with this technical session 5 of this conference. I will be moderating this session, though we were having 4 speakers in the start, but due to that, a little bit dilemma with timely arrival and, late arrival. So now we would be only restricted to 2 speakers, and they are available on site. First of all, let me introduce myself. I am Dr. Amjad. I am working as a senior research officer in National Space Agency of Pakistan that we call SOPARCO. I have a master and PhD in remote sensing from University of Twente, Netherlands. And I have been working in the field of water resource mapping, monitoring, land use, land cover, climate change, and RAD plus technologies in different capacities, in different role. And today I am here to moderate this session. So let me call the first speaker. Her name is Eileen Sol. She's from Argentina. And she will talk about the application of space technologies for mass balance estimation in Patagonian glaciers. She is an aeronautical engineer from National University of Technology in Argentina. She's teacher and researcher and director of Synthetic Aperture Radar Research Group. Ms. Eileen, floor is all yours. Thank you.
Hello, thank you all. This is not my presentation. All right, here we are. So many thanks. We are like in a rush. Many thanks, UNOSA, for this opportunity to tell you about some interesting facts about Patagonian glaciers. Well, I am Eileen, and this presentation titles Application of Space Technologies for Mass Balance Estimations in Patagonian Glaciers. Okay. Is this on? Yes. Okay, perfect. Okay, well, we see this picture and we can almost feel the cold. We see ice and it's cloudy, but those icebergs on the lake, they tell us something not so chilly. The retreat and disappearance of mountain glaciers around the world is the most dramatic evidence that Earth climate is warming, and it is doing at an accelerating rate. So this map shows the Santa Cruz River basin. Glaciers are located in the west part throughout the mountain range and are responsible of feeding those huge lakes. Just to have an idea, Argentina Lake, that the one in the bottom, is more or less twice the size of New York City. So this meltwater converges to Santa Cruz River and flows more than 250 kilometers crossing arid Patagonia to finally end at the Atlantic Ocean. It provides drinking water to the entire basin, and those are some of the most important cities located in it. Okay, this is the location of Los Glaciares National Park. It's located southwest Argentina. While ice melting is changing landscapes and can lead to floods and landslides. Tourism is strongly affected since trekking and boat trips become very risky due to the great amount of icebergs and crevasses. Tourism is the main activity of the local people, but most important, it impacts on the availability of fresh water. Well, glacier mass balance is the annual, this is a little bit of definition, is the annual balance between how much snow accumulates on a glacier and how much ice is lost through melting, sublimation, or ice belt calving in this accumulation zone and ablation zone. So in the absence of, of direct field measurements, mass balance can be estimated using an indirect method called the geodetic method, which consists of measuring changes in elevation in time using different digital elevation models. Our objective is to measure glaciers' tendencies by means of their mass balance, making use of freely available Earth observation tools and softwares and processing tools. So for this kind of analysis, we make use of satellite data from all available sources online. Although I have taken notes of many other sources that might be useful for me in this conference. Well, that is free optical and radar imagery, a global inventory of glacier outlines, digital elevation models, ISAT LiDAR elevation points, and meteorological data from satellites. Well, we see, since all this data comes from different sources, we have to convert all reference system, both horizontal and vertical, into the one selected. So we can then start comparing values once they are all referenced to the same datum. Digital elevation models were also co-registered. We also made a correction of the elevation values from these models according to ISAT LiDAR points on rocky fixed areas because of its better accuracy. Finally comes resampling, resizing, and it all ends into Python scripts. Oh, okay. Down. Thanks. Good. So regarding glacier boundaries, we delimit outlines with help from GLIM's repository of glacial outlines, but we still have to make some corrections to them. For this, we use SAR radar images that are best for this almost always cloudy environment, and also optical images of the closest date of SRTM acquisition, that is February 2000. And it is important to know that we only use space data of the end of the summer season, so we can make sure that there were no sudden snowfalls that might disrupt the values, the elevation values. Mass balance, well, this is some results of mass balance charts for the 4 glaciers under study during the period 2000 and 2015. Divided into ablation, accumulation, and total area. So bars below 0 means a negative mass balance, which means glacier volumetric retreat. The table shows the contribution to water levels due to the glacier shrinking, but it is related to Argentino lake levels because normally it relates to sea level, but it doesn't make much sense here. So they total almost 80 centimeters high. Meteorological data of the study areas provided by Terra Climate and NASA Power Project. So we see precipitation in millimeters for the same period divided into winter season and annual mean. Both slopes are negative, the tendencies, I mean. And surface temperature in Celsius for the same period divided into summer season and annual mean. And both temperature tendencies are positive. So we also, we can actually measure in a regular basis surface retreat. And from these measurements in time, we verify, of course, that glaciers are shrinking, but not only in surface, but also in volume. So the shrinking rate of this group of glaciers is around 500,000 square meter every year. So we see that mass balance is negative for all glaciers for the period 2000-2015. That can be associated with a negative trend in precipitation in winter and annually, and a positive trend in temperatures, mostly summer. We noticed that overall ablation areas retreated more than accumulation areas. We couldn't find an immediate direct relation between mass balance and meteorology, but as some authors have foreseen, poor precipitations during winter season along with high temperatures in summer ensures negative mass balance. And regarding to limitations, they become new challenges. So we do not dispose of elevation data of every year freely. We tried to obtain digital elevation models with INSAR techniques, but with really bad results due to the very low temporal coherence between images. So we need to find another ways to get elevation data from space for shorter periods, right? And although ENSO has been taken as a climate variable, we didn't find a direct relationship because of the aforementioned temporal spacing of the data. Elevation data for shorter periods of time will lead to better estimates of trends, of course. So we are on the way to standardize the methodology and data handling by moving towards encoding. Then this analysis can be replicable to all other glaciers in the national park. Of course, the statistics can help us understand the relationship between mass balance, surface retreat, and meteorology on an annual basis. It could be desirable also to estimate a reference value for mass balance for each glacier and as a variation rate. Also, and then generation of predictive models to estimate future glacier dynamics based on climate projection. Well, we show that visual stability of glacier fronts is not sufficient to evaluate the condition of a glacier. And well, there is a loss of drinkable water that, for example, now flows to the Pacific due to the change in flow direction as a consequence of glacier retreat. So flow is also changing. We think that a glacier response to local climate variation is not immediate, which means that, for example, a decrease in precipitation in winter won't be precisely noticed in next year mass balance. It might take more time to impact on mass balance measurements. So this is happening to Uppsala Glacier that used to be the biggest one. Okay, the picture on it, we cannot see it, but it's a GLOF, a glacial lake outburst flood that is starting to happen in many places. This is something new that we are seeing. This changes landscape suddenly and can lead to landslides and also floods. So tourist activities and navigation have to change continuously due to the great amount of icebergs. And well, the question is how much time will pass until Santa Cruz River flow measurements start falling, and of course, how much water do we still have there? Okay, this is an animation of a specific area of glaciers. This was the change of inflow direction that I was telling you. Glaciers used to be a natural dam, and since they retreated, flow changed their direction and now mixes with the salty fjords of the Pacific. So it's a loss of fresh water, very important loss. Okay. That's it. Thank you very much for listening and for a rush coming.
Thank you very much, Ms. Aline, for an insightful presentation about a very special, element of the Earth surface that we called glacier. And we can also call it very simply that it's the most serene and the most delicate part of the Earth surface. And you have, elaborated on the mass balance studies. So mass balance studies are very important, for in context, especially of glacier, because, water is the second most important element of the on the earth for the sustenance of life. So for that, if you want to have a good water availability, so you must know something about the mass balance studies that is related to the glaciers, because glaciers are vital to our water system. Two-thirds of the water of the earth systems are stored in the form of glaciers, and they are particularly helpful in even in regulating climate. And you might know that because in the in the Arctic, North Arctic, and then Antarctica, and in most of the glacier region, because of the white color, most of the energies reflected back into the atmosphere. So they are very helpful in even regulating the climate. So in addition to that, it can support many ecosystem writings, right? Start from the high ups, go you can go up to the even deltas. It can add a lot to the livelihood of the people, and beside that, it is really important for the tourism. We can, Madam Mandera can actually reflect on that as well. It can support biodiversity, and I always call it a red listed, earth feature. Like usually we call it red listed if there is an animal species, but I think this is also a red list, element on the planet Earth. With this, now let's, call the second speaker, Mandera Singh Sharishta. She's Senior Water Resource Specialist, International Center for Integrated Water Management, Nepal. She's a Senior Water Resource Specialist in SEMOD, and she has over 25 years of research experience that cover broad areas of climate services, disaster risk reduction, and water resource management. And she will talk about the increasing risk of glacial lake outburst, floods across the Hindu Kush Himalayan region. And let me tell you one thing, that we will having a question answer session in the end, because after concluding these two presentations, we will be having enough time to discuss the different matter that is related to the glaciers. Thank you very much, madam. The floor is all yours.
Thank you, Mr. Moderator, Mr. Dr. Amjad. Very good afternoon. How are we all now? Happy and content with the lunch that you quickly had and a very nice program that we saw this morning, going up to the community and seeing how they water function. So I'd like to thank the organizers for making that nice program and giving us that opportunity to really see for reality how it is on the ground and how water is being managed at the local level and how it's relevant to what we are doing in terms of space-based applications. So now today, my presentation, as has been said, is I'm going to talk about this increasing risk of glacial lake outburst floods in the Hindu Kush Himalayan region. Yeah, so I'd like to see a hand quickly of who are familiar with the HKH, the Hindu Kush Himalayan region. Yeah, I see two hands there. Yes, a few more, so 4 or 5. So that means I should, introduce to those that are not familiar with the HKH region, right? So what I will do is basically talk about, my presentation is going to be about first talking about where I'm from, my organization, and also the brief kind of outline of the climate conditions of the Hindu Kush Himalayan region, bringing it all into the context of GLOF. I think the previous presentation nicely kind of leads to what I am going to be presenting. And then understanding some of the cryospheric challenges, like we heard, in the Hindu Kush Himalayan region and how it is being managed. Then the case studies of GLOF from Nepal, Bhutan, and India. Then some of the mitigation measures, and I think it's important to see how we are really dealing with these risks. What are some of those structural measures, non-structural measures? And I'd also like to share with you and highlight the cryospheric program that we are having at ICIMOD, and then provide you with basically a summary of what I have to say. So ICIMOD, the International Center for Integrated Mountain Development. We're located in Kathmandu, Nepal, and we are a regional knowledge center, primarily focusing on the mountain regions of the Hindu Kush Himalayan region and looking at sustainable development of the region. So we work for 8 countries, our mandate. So those 8 countries are Afghanistan, Bangladesh, Bhutan, China, India, Myanmar, Nepal, and Pakistan. So these are the 8 countries of the Hindu Kush Himalayan region. So now let us look at what this region is really. So you can see a map here that shows you the extent of the Hindu Kush Himalayan region. The dark blue that you see basically shows you the Hindu Kush Himalayan region. It's the youngest geological formation. Yeah, it's the youngest geological formation, and it has high spatial variation in terms of the vulnerabilities that are there in terms of the physical as well as the climatic conditions. And this region is also known as the third pole. Yeah, the third pole, because it has the largest reserve of snow and ice outside the polar region. Yeah, so that's giving us the name as the third pole. Now, the climate context, yes, and there has been a study that was done several years ago. Let me just go back to those slides here. Yeah, one more back. Okay, here we are. So a review of the assessment. There was an assessment done of the Hindu Kush Himalayan region where we looked at various scenarios. So you see the RCP 4.5 and 8.5 scenarios here. But what needs to be taken into account is that when you're talking about a 1.5 degree world, yeah, the warming is likely to be more in the Hindu Kush Himalayan region. So it's likely to be more by at least 0.3 degrees Celsius. So that's quite alarming because the mountains are warming at a rapid rate. We have temperature dependent warming. That's the reason why it's more higher in the HKH, the Hindu Kush Himalayan region. So this particular study that we have, the HKH assessment, we call it the HIMAP assessment. This is available online, and you can download it from the link that is provided in this particular slide. So what does this mean in terms of greater warming in the Hindu Kush Himalayan region? Yeah, so primarily, we see that the precipitation extremes are increasing, and it is being more variable and erratic. And I think this is not an kind of a surprise, because this is true for many other regions. And that we are seeing that there is, like I said, temperature-dependent warming. Unlike what we saw earlier for Argentina and the region, we will see an 8 to 12% increase in precipitation in this region. Yeah, that's the scenario that we have. And what does that mean? That means that we are going to see more extremes that are going to happen in the region. And already we are seeing that. There's more high intensity, short duration storms that are already happening. But what does this mean for our glaciers? Yeah, that's the next question that we have. So the same study that was updated actually just last year. It was released, this updated study was released last year. We call it the HiWise report. The report that looks into the Himalayas in terms of the science behind it, and then the ecosystems as well as the cryosphere aspects of it. So water, ice, and the socio-economic and ecosystems. So that's WISE, that's what it stands for. So in a 1.5 to 2 degrees world, yeah, the glaciers in the Hindu Kush Himalayan region will lose 30 to 50% of their volume by 2100. Yeah. And then similarly, in a different scenario, in a 3 degrees world scenario, 55 to 75% of the loss, depending on location, and 70 to 80% in a 4 degree world. So basically, you're looking at huge losses that are likely in the future for different temperature scenarios. And so every increment of warming matters strongly for the region, definitely. And that you can see that 50% left at 2 degrees warming, 25 to 45 at 3 degrees, 20 to 30 at 4 degrees Celsius. What does that mean? Here, my presentation is on GLOFS, like was said. GLOFS is an acronym for Glacial Lake Outburst Floods. So that means that we are going to be, it's likely that there's more glacial lake outburst floods that are going to happen and that we need to prepare and mitigate to build resilience. So why is it that we are going to have more GLOF? Well, we already saw that the temperatures are rapidly increasing. The glaciers are retreating fast. That means the number of lakes that are there available are increasing in size. So the amount of volume of water stored behind these lakes are increasing rapidly. And these are forming, great danger to the people in the region. So this region is already seeing, many different high mountain hazards under the climate change scenarios. So you're seeing landslides, you're seeing snow avalanches, floods, and also its impact downstream to the society as well as the infrastructure. And here you can see that this particular diagram here, the framework of disaster risks being a function of 3 elements. We are talking about the hazard itself, that is the glacial lake and the hazard itself, and then the vulnerability and as well as the exposure to these hazards. Yeah, so it's urgent that these disaster risks, imminent risks, be reduced. And what needs to be also here considered or taken into account is that there is increasing cascading impacts. And I think this came out quite strongly on the first day itself, where we talked about the cascading impacts in one particular hazard leading to another hazard. And here in the high Himalayas, it is not only the snow avalanches. For instance, just a few weeks ago, there was a huge avalanche in one of the lakes in Nepal, which led to a glacial lake outburst flood. This avalanche basically fell into the lake. It increased the water levels in the lake and basically overflowed. And there was a huge glacial lake outburst flood. And similar kind of events are likely that we will be seeing in the region. Yeah, so I'll not go into the details of what that small slide says, but primarily to look into seeing, the understanding of the cryosphere change and also managing the risks in the Hindu Kush Himalayan region. So what ICIMOD has done in the past, in fact, the last 2 or 3 decades, 2 decades at least, starting from 2000 onwards, we've made inventories of various glaciers and glacial lakes of Nepal, but it's not only of Nepal, but of the entire Hindu Kush Himalayan region, and also looked into some of the risk mitigation measures of some of the glacial lakes that are available or that are present in the region. Now, we've also developed a methodology for glacial lake risk reduction and as well as assessment. And then this inventory that I just mentioned, where we are supporting the government of Nepal and other regions. So we have the glacial lake study by ICIMOD. Here I'm showing you the series of inventories that has been done. This has been done using various data sets, various satellite images, primarily the Landsat images, and where starting from 2001, so there was a repeat inventory in 2011, then 18, and then 20. So what did this enable? Why should we be doing so many inventories, I guess, would be a question that you may have. So this primarily looks into the change in terms of the glaciers. In terms of the change detection is very important to see how these glaciers are retreating and the formation of these lakes, as well as the size in terms of the changes that you see in the along with time. Yeah. So with that, I mean, I'd like to highlight some of the key challenges and gaps that we have course, definitely, we've been talking about the need for looking at in situ data and observations. And it is no surprise that the climate observing networks in higher elevations, are very, very limited. And I think this is also true for many countries around. Yeah, I see Eileen shaking her head. So Argentina is probably, also there in terms of very poor observing networks in higher elevations. There are efforts being made, but again, not quite adequate for high observations to better understand the changes that is happening in the region. Then the lack of credible data and information. Yeah, so whatever data is available is also not only limited, but also it's shared on a very, very kind of not widely shared, let's say limited sharing. Yeah. So across institutions, primarily if it were to be doing with transboundary, then that's even more challenging, transboundary sharing. In order to reduce the risks of glaciers and glacial lake outburst floods, it's urgent that we put in early warning systems in the mountains, the high mountain areas, to inform the people living in the downstream, as well as the various infrastructures that are in place. However, there are limited installations of these early warning systems. I will be showing you some of the examples of the early warning systems, in fact, in the region, and then its effectiveness and whether it was actually installed. Yeah. In terms of the diversity of the knowledge and the capacity across the region, that varies. I talked about 8 countries. So the experience that exists from one country to the other varies. For example, we have China and the China Meteorological Administration, as well as different organizations, have a lot of knowledge, experience, data, tools, methods, which they can share with other countries. Similarly, if you're talking about Nepal or Bhutan, for instance, there is limited capacity in terms of both monitoring of these glaciers as well as the data availability. Then another important aspect, particularly since I'm talking about also the risks involved due to the glacial lake outburst floods, it has to be gender responsive, I guess, tailored to the needs of the users. Yeah, because many of these events, the glacial lake outburst flood events, that happen primarily during such kind of disasters, not only GLOFs, but other disasters as well in the region. It's the women, the children, the elderly, the marginalized that are the most impacted. So there is differential impacts of disasters for which concerted efforts need to be made in terms of making it more gender responsive and looking into the needs of different audiences. So I will share with you some of the different glacial lake outburst floods that I have mentioned in the abstract. The first is the Bhutikoshi glacial lake outburst flood that occurred in Nepal. And here, this is a transboundary glacial lake outburst flood that has happened. The lake itself, the glacial lake, is in China. Yeah, but the damage after the burst is in Nepal. Yeah, so there's this urgent need for sharing and having an early warning system put in place for really informing these communities as well as these people living downstream. So you can see in this particular slide here, oops, let's go back one more. Before and after images, yeah. Yeah, yeah. Hold on. No, it's going back. Let's go in front. Yeah, there you go. So you can see the 2 slides there, before and after. Yes, so before the glacial lake, you can see the hydropower project, the dam site. Yeah, and then after the glacial lake outburst flood occurred, you can see the damage. They completely destroyed the hydropower project. In fact, this particular project This was about a 45 megawatt hydroelectric power project was shut for at least 4 to 5 years to bring it back into operation. So there was huge damage. There was no early warning system in place, a formal early warning system. But again, what matters is also the communities living upstream and downstream. So through these informal channels, also the people living in the downstream were then informed about this big flood that is coming down the river. And so the people were aware, and fortunately there were no lives lost. Yeah, so in the absence of a formal early warning systems, communities do get together to inform each other. Yeah, so this is one example. Okay, the other example that we have is again from Nepal. This is called the Melamchi Glacial Lake Outburst Flood. And this in particular, I wanted to share with you because the glacial lake itself was in Nepal, but again, this was this resulted in many cascading hazards. It's amazing what, really it triggered. A small glacial lake occurred in the about 5,200 meters. This resulted in a huge landslide. Yeah? The landslide basically came down and then it formed a dam across the river. Yeah, then you had a landslide dam formed and rivers that were, at the back. The river water was accumulated at the back. Yeah, and then sudden breach of this landslide dam, then more floods going down the hill. Yeah, so there was these cascading impacts of the glacial lake outburst flood that occurred. And as a result of this, I mean, unfortunately, in this case, there were 25 plus people who were killed. But again, even though there was no early warning system in place, again, there was this informal mechanisms of people living in the upstream, informing those in the downstream to get better prepared. Yeah. So, so this is another example that I had to share with you. The next example is a glacial lake outburst flood from Bhutan. This is called the Lemthang Sho. Sho in Bhutanese language means lake. And this is at an elevation of above 4,000 meters. And again, this is an example where I mean, there were a lot of damages, direct as well as indirect, as we call it. But fortunately, people were warned of this, the glacial lake outburst flood that occurred, and that the damage that could have been incurred was avoided. Yeah, so you can see here, the two images, one with the lake and the other where the whole water has been drained. Yeah. So the other example that I have is the most recent example. Yeah, this is from the South Lonak Lake. This is from India, the glacial lake outburst flood. I'm sure some of you present here, and as well as online that are listening to this presentation, have heard about this glacial lake outburst flood that occurred just recently in 2023. This was in October of 23, where this lake suddenly burst and brought in huge damage in the downstream. So the analysis of the satellite images, primarily the Landsat image, as well as I think there was this other image, Corona image, 1977, that showed that this lake had rapidly increased in size, from a size of about 17.5 hectares to 81, more than 80 hectares over a period of about 30 years. Yeah, so you can see that there was huge, the lake had really kind of increased in size, but unfortunately there was no early warning system that was in place. So because there was no early warning system in place, this particular glacial lake outburst flood resulted in huge damage to the hydropower project, the Tista hydropower project that was about 1,100 megawatts, and washing away a lot of different infrastructure, and more than 70 people were killed. Unfortunate. This particular glacial lake was in the high danger list, but irrespective, the early warning systems were not put there on time. Yeah. So with those four examples, I wanted to show you the distribution of the glacial lake outburst floods in the Himalayas. My colleagues at ICIMOD have studied this distribution of GLOFs across the Hindu Kush Himalayan region. And according to the study and the inventory that has been done, there are various types of uh, glacial lake outburst floods, the triggering mechanisms, as well as the total number of glacial lakes that have occurred in the region over the last 50 years is more than 400. Actually, it's a large number of glacial lake outburst floods that have happened in the region. Yeah. So there's more than 400 glacial lakes that have occurred. Yeah. So this then there's another slide here that basically shows you the different types of dam that is behind these glaciers that kind of breached and resulted in the outburst. So there is a I'm not sure if this I have put it here, but we do have a kind of a dashboard which shows the location of these glacial lakes. Here, the attempt was to try to see the slide here that you are seeing. It was to see, the different types of damages that occurred and whether and when and what kind of the glacial lake outburst floods occurred. So in terms of the different, the more than the 400 different glacial lakes that have occurred in the region, we have come up with an estimation of the socioeconomic impacts of these glacial lake outburst floods according to the countries, which you can see here. And then the total economic damage in the region accounts to be more than 600 million over the last 50 or so plus years. Now, like I was saying earlier, there is a need to reduce this disaster risk. And this framework that you see, yes, this particular one I have taken from an older kind of report on the SREX report on extremes, where you see that the disaster risks is again a function of the hazard and then the vulnerability as well as the exposure. And there are different spatiotemporal parameters. Like, for instance, in the science and technology, here we are talking about space-based applications. We have also, the ecosystem resilience, the need for financing, the knowledge that is required, the partnerships, because one cannot be working in isolation, and then gender mainstreaming. Governance is equally important, having proper institutions and early warning systems to minimize the disaster risks. So I'll give you some examples of some of the mitigation measures, primarily the structural measures that has been in place. This is for Nepal. So this is called the Shorolpa Glacial Lake Risk Mitigation. And here the lake level of the Shorolpa Lake has been lowered by more than 3 meters. There were several attempts, first siphoning of the water, and then there was also this natural, the drawdown of the lake through this trapezoidal channel that was built. And an early warning system, like you see here, was put in place to inform or warn the people living in the downstream. So this has worked so far. This is the largest lake in Nepal. It holds water of more than 100 million meter cubed behind this dam. So in this lake. So it's a huge lake and did create quite a lot of kind of scare to the people living. But since some mitigation measures have occurred, the risks have been reduced. And then the other, again, example is the Imja Glacial Lake Risk Mitigation Measure in Nepal again. And here, this is another lake that's above 4,500 meters. And here in this lake, also the level has been reduced by 3 meters. Yeah, and an early warning system has been put in place. So when I say early warning system put in place, this requires definitely, also working together with the people and the communities living along the river to ensure that they understand, what to do and where to evacuate should there be a glacial lake outburst flood. Now, another example that I want to share with you on the risk mitigation. There are many examples actually. This is from Bhutan. This is called the Thorthorming Sho Glacial Lake. And here, this is quite interesting because this is a kind of manually, basically the water level in this lake was reduced lowering the lake by 5 meters, it says, and a comprehensive early warning system that has been put in place. And in this particular basin, there are hydropower projects of capacity of more than 2,000 megawatts. So there's large amount of investments as well as people and community living in the downstream. So what are some of the other measures that are being put in place apart from the structural measures that I just mentioned? Of course, there are these monitoring of the glacial lakes that are ongoing. And this is both by ground-based sensors as well as satellite-based observations. So when I say ground-based sensors, we are, the water level in these lakes are being monitored. There have been radars for looking at, ways of seeing what the water level changes in the lakes are. So these where the radar sensors are there, and also looking at the changes in terms of the temperature and then the amount of precipitation. Satellite-based observations, yeah, different imageries we are looking at on a regular basis, and also looking at, satellite-based estimates in terms of precipitation and other parameters. Yeah. The other example that I have is the mapping and monitoring of the glacial lakes. So when I say mapping and monitoring, this includes the inventory of the various glacial lakes that exist in the Hindu Kush Himalayan region, the monitoring through, again, the regular inventory that we are doing and seeing how it is growing, and then the risks behind it in terms of also looking at models and trying to see what the scenarios would be should the lake burst and what kind of impacts it would incur in the downstream. So with those examples, I want to also share with you some of the activities that ICIMOD is doing, particularly on the monitoring of the cryosphere in the Hindu Kush Himalayan region. So we have a three-pronged approach. When I say a three-pronged approach, we're looking at field-based monitoring. So we have sensors on the ground. Particularly, we're working together with the mandated organizations, the hydromet agencies. In Nepal, it's the Department of Hydrology and Meteorology. In Bhutan, it's the National Center for Hydrology and Meteorology. Similarly, in other countries, in terms of looking at field-based monitoring. And then looking at also, use of remote sensing, which I just mentioned already, looking at the various satellite images and looking at the inventories of these glaciers. And then the third part is more the modeling part, which I also referred to in earlier. Yeah, so that's the kind of a three-pronged approach that we are doing. And so you can see that there are these examples from the ground in terms of in terms of the monitoring that is occurring in the region. Yeah. Just to emphasize that it is important that we work closely with these organizations and agencies in terms of both an individual capacity building as well as the institutional capacity building in cryosphere monitoring in the Hindu Kush Himalayan region. So here this includes, working closely with the different universities also and these other mandated organizations to co-create some of the cryospheric data and information and making that available, and also working on the cryosphere monitoring. So on a and that's quite a difficult task in terms of every year my colleagues go in the field expedition and to look basically at how these stations are performing in the field and whether there are any problems, and then collecting that data from the field. And there have been instances where it has been quite risky, I must admit, going to the field. And so this is a very difficult kind of a aspect of cryospheric monitoring in terms of in situ monitoring. Yeah. And so this was a recent study that was done. I say recent, a couple of years ago, but this kind of shows you the various the glacial lakes that are in Nepal, particularly in the three basins, Karnali, Gandaki, and the Narain, the Koshi basin. And in total, Nepal has 21. When you say PGDLs, is potentially dangerous glacial lakes. Yeah, so that's China has 25 and India has 1, according to the study and the criteria that we have got. Just to quickly kind of jump in, share with you the approaches for GLOF risk assessment. So there is a detailed kind of a methodology that has been put in place, which is being followed for the assessments in the region. And in terms of the physical vulnerabilities, there's also the, including looking at collecting data that includes bathymetric surveys of these lakes. And this is also very challenging and quite expensive, actually, going high altitude and collecting these lakes and doing the socioeconomic and vulnerability assessments. Yeah, so we have this long-term cryosphere program in the region, particularly in Nepal, with the Kathmandu University, as well as the Department of Hydrology and Meteorology. This was initiated way back in 2011, and we continue to be working on this and providing these data to the WGMS, yeah, the World Glacier Monitoring Service. And apart from this, like we heard today, it is important for the community engagement. So together with the community, there's also a participatory hazard risk assessment that is done to understand the local knowledge that exists and how that can be integrated with the early warning systems and the science-based information that is being generated to ensure that the risks from these glacial lake outburst floods are minimized. So in this here, a photo that you see here, the image that you see, it's the people in the community basically making their own maps and better understanding the hazards and the risks behind it. Yeah, so with that, I just would like to take a minute to share with you that ISIMO has now embarked on having a new strategy in place. So we call it the 2030, ISIMO 2030 strategy. And our main vision is a more greener, more inclusive, and climate resilient Hindu Kush Himalayan region. Yeah. So here when we say greener and more inclusive, we are more looking at, being more nature positive, cleaner, carbon neutral, as you can see, more resource efficient, inclusive in terms of being gender sensitive, gender responsive, bringing in the youth to these studies. I think this is also important in terms of encouraging students and providing equal opportunity and more climate resilient. And this could be through many different approaches, including policy interventions. So we are now having a very focused program in managing cryosphere and water risks, which my colleagues are working on. And in summary, I just want to say that, yes, the glacial lake outburst floods are, becoming more frequent, resulting in very huge losses in terms of lives as well as properties and infrastructure, where there is a need to look into more climate resilient infrastructure. So ISIMO is working with also the government to put in place a climate resilient guideline, yeah, particularly for the infrastructure, the hydropower. There's, of course, definitely the need for systematic and continuous monitoring of these glaciers, and the generation of more robust knowledge as well as data that is being generated. Then along with that, building capacity is important. And whose capacity would be the question. So yes, it is at different levels of the hydromet agencies, the mandated organizations, the research organizations, but also at the local level in terms of raising the awareness and making them a part of the whole process. And the timely communication and dissemination of early warning is essential. And this is where I think this was also came up in some of the presentations that we heard in terms of ensuring that it needs to be understood by the local communities. So language is important. How do we ensure that we have it in the proper language, as well as how do we make this information more relevant as well as understood, packaged in such a way that it can be taken by the communities. We call it the last mile connectivity. And then as most of these hazards are transboundary, space-based technologies do provide a lot of opportunity to understand the spatial extent as well as looking at the temporal and for which transboundary collaboration is required. So there is the requirement of intergovernmental cooperation and collaboration, particularly putting in early warning systems and sharing knowledge, and also a mechanism in place. Yes, there's a lot of kind of advancement in terms of looking at ways to share data and knowledge and products and best practices. But mechanism for sharing of the early warning would be something that would be of priority to the countries. And climate risk assessment is a prerequisite. I say that because now many of the infrastructure that are in place are facing a lot of challenges in terms of these increasing floods and risks, because they have not been designed looking into the future climate scenarios. The 100-year that for which the infrastructure was designed is not anymore the 100-year flood that is going to be happening. So because of the changes, the climate change. So this now for the new infrastructure that are to be in place, it has to be more climate resilient, for which there's a need to be looking into risk assessments, particularly focusing on climate, and that many of these policies and the work that we are doing has to be in a way that is aligned, as well as linking it to the broader kind of local and global targets. And here I would like to bring the Sendai DRR target, particularly the target G, that is the early warning systems, making it multi-hazard and available to everybody, just leaving no one behind, basically. And then looking into ways of better cooperation and collaboration globally as well as regionally in the region. So with that, I thank you all for being patient and listening to me, and I hope it has been a fruitful presentation for you all. Thank you.
Thank you, Mandira Singh Sharista, for educating us more on glacial hazards. And you have very nicely covered the whole spectrum of the glacial hazards. You have really started from the very basic, and then you have reflected more even on the how to identify it, and then later how to actually address this problem through a participatory role of the community. And indeed, glow-off and avalanches are the most destructive type of hazards in the world. Now, we are really very lucky to have the opportunity to listen to Professor Yang Hong. He will talk about, I hope Professor Yang is available online. Okay, fine. Okay. He will reflect on remote sensing and hydrological modeling for assessment of water resources and cascading geohazards in Peru. He is having quite a number of roles. Let me reflect on that. He is Professor of Hydrology and Remote Sensing, Gallup-Gilly, Chair and Presidential Research Professor, School of Civil Engineering and Environmental Sciences. He is an Adjunct Professor, School of Meteorology, Gallup-Gilly College of Engineering, University of Oklahoma. He is having a role of Director, Hydrology and Water Security Programs. Beside that, he is also looking after the role of Director of Hydrodros Laboratory. He is working as co-director of Water Center for Research and Advanced Radar Research Center. Professor Yang, floor is all yours.
All right. Good afternoon, everyone. I hope you can hear me.
Yes, I can hear you. You're
All
loud and
right.
clear.
Okay. Can you see my slides as well?
Yes, your slides are very clear.
Okay. Thank you so much. I apologize. I couldn't be there. The beautiful country, Costa Rica. I remember in 2006, the IEEE, we had a meeting at the San Jose when I was working at the NASA Goddard. Well, we just heard two previous outstanding talk. One is focusing on Southern Andes, and the other one focusing on HKH, the Himalaya. My talk is going to be talk about the Upper Andes, mainly in Peru. My talk is more than glaciers. I like to talk about how we can use the remote sensing data to map glacier and the snow, and also how we can apply hydrological model to predict the future water availability and the cascading geohazards such as a flooding, a drought, even landslides in Peru. All right, let me move to the next slides. Okay, so why we study high mountains? Well, because it's really challenge for not just for science, remote sensing, also is important for the societies. So the high mountain Andes is the second largest mountain after the Himalaya. In this talk, I like to focus on Peru. So far, Peru has limited capacity in research education in terms of the satellite remote sensing, climate change impact on hydrology. So with the funding from government agency and also from the country of Peru, we have a project looking at these issues. Well, we have two particular focus region. So one region is upper in the high mountain, high terrain. It's about 4,000 meters. The province is called Puno. So this is the big lake, which is impacted by the directly by the mountain glacier snow melting. The other focus region is the city in terms of the Lima and also the Arequipa cities. So these are kind of a downstream from the mountain all the way down to the oceans. All right, I like to talk about the objectives. So we have two specific objectives. The first one is to develop the Peru Joint Center of Earth Observation and Prediction for SDG, by sharing expertise and doing capacity building in remote sensing and hydrological modeling. And the CEOP, the Center of Earth Observation and Prediction, also will act as a regional hub, which will conduct applied research and also promote collaboration among the local government, university, NGO, and the public to support the UN SDG 2030 in Peru, with particular focus on the water, SDG 6, and the agricultural land, SDG 2, and the 13 climate, ultimately sustainable communities. For this project, we have specific 8 research tasks. Let me just quickly go over. Number 1, we like to utilize multi-source satellite and also climate analysis to build a water cycle database from 1980 to 2025. So what we talk about water cycles, precipitation, soil moisture, stream flow, those informations. Then particularly relevant to this session is we're going to produce records of a cryosphere database from various satellite missions such as Landsat, MODIS, Sentinel, and GRACE year one, we like to build up the particularly the glacier and the snow cover from 2000 to present. Then with those water cycle database, we're going to apply hydrological models to do a water modeling and the land cover and the change analysis. We will also identify key ecosystem conservation, location and hugely impacted region in Peru. Then we will also model the land ecosystem, the vegetation. Finally, we'll integrate those remote sensing data, ground data with the hydrological model, land model to design and implement a digital platform that will integrate satellite data and model, ensure resilience to potential climate change impact. So finally, as previous speaker emphasized, we also host workshop, education, and transfer technology, capacity building. So specifically on the task one, we utilize a lot of remote sensing data and reanalysis. In particularly, we're using the global precipitation GPM and the reanalysis ERA5, CHIRPS, CMORPH data, SMAP, soil moisture models. They recently launched a SWOT model. Also, some other globally available in situ or reanalysis data includes GPCC, PISCO, to build the water cycle database from 1980 to 2025. So it's about 25-year database. On task two, this is specifically regarding the slow cover and the glaciers mapping. And also we use GRACE data to look at the total water storage change over the last 20 years. So in order to produce this database, we utilize a lot of remote sensing images and some other data sets from 2002 to present. So those are the information database we used to generate this glacier and the snow cover database over last 20+ years. Just in case anyone interested in this database, you can always feel free contact me, and we'll be happy to share this with you. So after the task one, task two, we have those database, right? Then we're going to use this modeling framework. So the left column is more database, right? Then the middle column is more multi-scale hydrological modeling, including a hydrological model, also the landslides models. I heard a lot about landslides from the previous two talks, which quite true in those complex mountain regions. We often have cascading hazards, either triggered by rainfall, by extreme storm, or triggered by glaciers outburst, or triggered by early spring, summer slow meltings, which cause the cascading water-related hazards, too much water floods, right? And also the landslides as well. But we need to set up this model framework at multiple scales. So the hydrological model is at 1 kilometer spatial resolution, and is a landslides model, we're looking at 30 meters and 90 meters over the regions. And finally, we're looking at the the user interaction, application, and looking at how the risk and those disaster alert and water availability. Those are the user communities engagement on the right columns. Alrighty, just over the last 2 or 3 year research, we already besides the database we built up, we also published a few publications. But here we'd like to just share one paper. This one cross-examined the precipitation data from local rain gauge, from the satellite remote sensing, also from the climate weather model WRF simulation over South America region, across the Pacific coast and Andes. So we set up this region for weather and climate modeling is beyond the Peru countries. It's a bigger, broader region. But when look at the precipitation data, we specifically compare the NASA global precipitation GPM emerge. We also look at the reanalysis database, the multi-source rainfall data, and compare with the WRF model simulations over these regions. Those are the results. We this is the first research been done looking at over this particular region. Then we look at the sub-daily time scale, like 6 hours, 3 hours, because this is relevant to extreme events, flooding and landslides. So we look at the sub-daily 6 hour hourly time scales. Finally, for water availability and the drought, we look at the database at the monthly time scale from 2010 to 2019. Those are the statistical results. So the conclusion is, this region is a challenge to remote sensing, also challenge to weather climate modeling. We also has a limited in situ observations. So the best way to develop to develop a best possible database is to combine the in situ whatever we can have, also with the remote sensing data, and the weather, the climate modeling results. So we call a multi-source database we developed over this particular region from 2000 to 2024 this year. So after those database, we are utilizing this research framework from a mesoscale down to a hydrological 1 kilometer scale, then down to the landscape 10 kilometer street level scales, looking at how those changing water, changing precipitation pattern, changing glacier recovery, slow melting, impact the subsequent water availability and hydrological extreme events such as flooding and also the landslides. This is a hill slope landslides models we developed for this project. So we look at particular this region. This is the basin, and we have 1 or 2 stream flow gauge station. We did the simulation, calibration looks promising for this research framework. I'd just like to briefly talk about the hydrological model we used, which is the CREST model. stands for coupled routing and access storage models. 3 soil layer, cell-to-cell distributed model. This model was jointly developed by our university and also with NASA Goddard 15 years ago. This CREST hydrological model has been widely used by global users, public applications. So far we did a simple search. We found over more than 100 publications and over 5,000 citations using this CREST model application worldwide. In addition to the, the past, the current, we also look into how, the future climate change will, impact this region. So we work with climate scientists. We set up the climate projection over entire South America at 1 degree resolution. But over this region, focus region, the resolution is at 5 kilometers, so which is pretty high resolution for climate model. We use 2 different scenarios, SSP 8.5 and SSP 2.5. So this one is moderate and this one is a high emission scenarios.
Professor Yang Hong, sorry for interruption. I hope you are already concluding because we are a bit.
All right. Let me quickly just.
Okay, yeah, you can maybe take another 2 minutes to conclude. Yeah, thank you very much. Thank you for listening.
So the quick summary is we have seen the future, rainfall will decreasing, but the intense rain the frequency of rainstorm will increase, and the impact for runoff is the total runoff water availability will be reduced in the futures. And likewise, in terms of the capacity building, we did a mutual visit, and we also host a workshop and capacity building with the Peruvian Institute. So this is my final slides. I guess I don't have time to read, but I just leave it here. Thank you so much for the opportunities.
Thank you, Professor Yang, for sparing time and reflecting on the topic. In the end, I would like to thank UN, PSIPW, ICA, Costa Rica government for providing us opportunity to reflect on this important topic of glacier monitoring. My special gratitude to the audience and the speakers. Thank you very much. We are going to start the next session immediately. So what you can do is you can get a coffee and you can just bring it back to the session, and we can just straight away continue with that. I'm afraid that we will not be having a formal question answer session. However, you are most welcome to ask question in informal way from the the presenter available on site. And for the online speaker, you can maybe put your question in the form of a chat, and we will try to furnish the response as soon as possible. Thank you very much.